All right. So just a reminder, the midterm will be available tomorrow sometime. I'll send an email. You can download it anytime you want from tomorrow till 5 days from tomorrow and work on it for 6 hours, contiguous block at your convenience. Last time we started talking about context-free grammars and context-free languages. This is chapter 2 in the book. Of course, we also did some stuff ahead of chapter 2, Turing machines, undecidability, the halting problem, and so on. But as far as the test, I don't play gotcha with you. I want you to do as well as you can. So we're going to only cover in the test what we covered through today, and in fact focus mostly on what we covered a long time ago, namely finite automata, regular languages. We'll touch on context-free only tangentially, because we just did that for the last couple of lectures. So context-free grammars, a set of variables, a set of productions, substitution rules to replace things with other things. And so, for example, you can do sigma star using a grammar like that. All possible strings will be generated here. Or you can do other kind of derivations. And we said here's a context-free grammar that will generate palindromes, strings that read backwards and forwards the same way. Pretty easy, only a few rules, and you get a lot of mileage out of these grammars. Another example was all possible ways of properly nesting parentheses. 3 rules get you the job done. You can juxtapose parentheses, you can nest them one deep, and if you apply that rule recursively, you can nest them arbitrarily deep, and you can get all possible well-formed nestings of parentheses with just a few, 3 in fact, context-free rules. So you can see how powerful these grammars are. Here's a grammar that generates all valid regular expressions. Any questions about these examples or what these grammars are, what they do, how they work? Just keep applying the rules. In what order? Any order you want. Whenever a rule is applicable, you can apply it right there and then, or any other applicable rule instead of that one rule. And the language generated by the grammar is all strings that could be generated by some sequence of substitutions or productions. Pretty straightforward. I'm going to skip on the subject of ambiguity because it's not as relevant to the midterm. But we'll get back to this. I'm going to skip a few slides here and talk about pushdown automata instead. So pushdown automata is basically a regular finite automata, but we give it a stack. So now we give it some memory. Remember, finite automata doesn't have memory, it just has states. You can change states, but there's only a finite number of states. So it has a finite amount of memory. And that's why we call it a finite automata, actually, because it has a finite amount of memory, a finite amount of states. But if we give it an unbounded amount of memory, like a stack, we can push and push and push onto the stack and also pop from the stack. Now it's got some scratch paper, extra memory, unbounded memory, potentially, to work with. And it can do things all of a sudden that a finite automata cannot do. But basically, it's just a finite automata with a stack. So it has all the features of a finite automata plus 1. And the same features. The finite automata, just to remind you, you have a set of states, you have an input alphabet, and now you have a stack alphabet because you have a stack. And the stack alphabet could be different than the input alphabet. It may be the same, but you have the option of having the 2 alphabets not be identical, potentially. You have a transition function, and this time transition function is a bit more complex. It doesn't just take you from a state and a symbol to another state like a finite automata. It also depends on what's at the top of the stack. So it's crossed. The state that you're in is crossed with an alphabet symbol, but it's also crossed with a stack character, whatever is at the top of the stack. And that gets you to another set of states. Now, non-determinism is built right into the definition here. When we define finite automata, we didn't use the power set construction here in this definition of the type of the transition function delta. But here we look at all possible next states, all of them, not just a unique one. And why is that? Finite automata, we define it deterministically, and later we proved a theorem that if you have a non-deterministic finite automata, it has the same power of some other deterministic one. So non-determinism is not a superpower. It doesn't buy you anything extra in terms of recognition. It could buy you some extra in terms of efficiency. You may need less states if you go non-deterministic. But with pushdown automata, it turns out that non-determinism is essential. It is a superpower. It gets you more. You can do more with non-determinism when you have pushdown automata. And that's why we built it right into the definition here. So you have states, and you have an initial state. You got to start somewhere. You have final states, could be more than one, and they're denoted pictorially the same way as with finite automata, ovals and arcs and little caret going into the initial state, and the double oval states are final states. There could be many of them. And so a Pushdown automata is simply the sixth tuple, and that's what it is formally. And again, I'm highlighting the fact that non-determinism is built right into the definition. Any questions so far? So it's just a finite automata plus a stack. Okay. So a Pushdown automata can use its stack as a first in, first out, a last in, first out LIFO kind of storage. A queue would have been first in, first out, FIFO, but this is LIFO, last in, first out. So you can push on top of the stack, pop from the stack, but you cannot go into the middle of the stack and take something away. It's like this stack of trays in the cafeteria. You take the top tray, and that's your tray, or a stack of plates, at a restaurant or a buffet or cafeteria. You take the top plate. You can't take a plate from the middle of the stack, otherwise something terrible may happen. Like the whole thing will fall over. But same with a stack here, just you can access the top with a push or a pop, and you can keep popping and get deeper into the stack, but everything you popped is gone. It's always the top of the stack that you're looking at. By you, I mean the read-write head that points to the stack, this guy here. And of course, on the input, you go only to the right. It's a one-way machine. And acceptance, let's just say, by final state. If you enter a final state, you accept. It doesn't matter what else is on the stack. You can also define acceptance by empty stack, but it's equivalent. When you exhaust the stack, you say, okay, then I accept. But yeah, here we'll just say, if you go into a final state, you're done. You accept the string. That string is in your language. Same as finite automata. Now, you can make the PDA specifically deterministic by restricting the transition function to only go to a unique single next state, not to multiple ones. So a deterministic PDA, Pushdown automata, is a special case of the non-deterministic one where you only have one choice of what to do next. Same for a finite automata, except here, if you use non-determinism, you can achieve more. And we'll give some examples later on. All right. So there's a theorem that says if a language is accepted by some context-free grammar, it's also accepted by some Pushdown automata. In other words, it's a complete characterization of regular, just like we had regular languages are equivalent to finite automata. For every finite automata, there's a regular language that it accepts, and for every regular language, there's a finite automata that accepts it. Here, the characterization between the context-free languages and the machines is pretty much the same, except that the machine now is not a finite automata, it's a Pushdown automata. So for every context-free grammar, its language, the language that it denotes or produces or generates, however you want to think about it, is accepted by some PDA, by some Pushdown automata. And vice versa. If a language is accepted by some PDA, its language of that PDA is necessarily context-free. That is, there must be a grammar for it as a context-free grammar if some PDA happened to accept it. Now, we're not going to prove these two theorems in great detail. They're a little bit technical, and it's probably more work than value in trying to prove these things, but I'll give you some intuition of how it works. A PDA can implement a grammar by one production at a time, picking an non-deterministic production, matching the first variable of that production against the character in the input right now that it's seeing. Doing that match, firing that production, but pushing the rest of the production characters on the right-hand side onto the stack, and now it has to recognize the rest of that. And it keeps going. So it's non-deterministically executing productions and matching them against the input, firing only valid productions. So I'm sort of giving you the outline of this proof, but it's not worth nailing down all the details. It's just an intuition. How many have some vague idea of what I'm talking about? A few people, okay. Yeah, it's fine. But remember these theorems. You don't have to know the proofs for them. I mean, the proofs are in the book. You can look it up and go through them. It's only a page or two. But the theorems are still important. So know that if you have a Pushdown automata, there's some context-free grammar that accepts its language, and vice versa. If there's some context-free grammar, there must also exist some Pushdown automata that accepts the language that context-free grammar generates. It's a complete characterization. One set denotes the exact same objects as the other set denotes, namely the context-free languages. All right, so that's what this characterization is. So they're equivalent. So just like we had finite automata equivalent to regular languages and also to regular expressions, here the equivalence is about grammars and pushdown automata. Okay, so I'm saying whenever you have one, you have the other that does the same job, and vice versa. Any questions about that? How many understand all of this? Never mind the exact proofs, just, okay. Any questions about that? So if I say consider an arbitrary pushdown automata, you already know that this language is context-free. If I say here's a context-free language, you already know that some pushdown automata must accept it. Which one remains to be seen, but there exists one that does the job. So that's simple consequences of these exact characterization. All right, let's prove some more theorems. These ones will actually prove. So the context-free languages, they're closed under union. So the union operator preserves the property of context-freeness. In other words, you take a context-free language, take another context-free language, take the union of all these strings in the two languages. The resulting union language must also be context-free if each one was to begin with. How would you prove that? I'll give you a hint. It's not hard. So if you think going some complicated path, you don't have to. Yeah. Yeah, so one way to do it is you can basically bash together the two PDAs, the two pushdown automata. You can create a higher level pushdown automata that non-deterministically, at the beginning, when it fires up, either starts executing the first one or the second one, non-deterministic, and keeps executing that one and never jumps back. So at the beginning of the execution, you pick which subroutine PDA you want to choose to execute on the input string and fire that one up and stick with that. If it accepts, accept. If it rejects, you reject. How many see this does the job? It's the union. Because non-deterministically, you're picking one or the other, so you're essentially picking both. You're non-deterministically branching and trying both. And if one of them accepts, you will accept. Because what's the definition of non-deterministic acceptance? It is bifurcating long tree instead of a path of a computation. So if one path leads to an accepting state, the whole thing accepts. By definition, that's what non-deterministic acceptance means. If you succeed somewhere, the whole thing is good. You succeed everywhere. Even if some paths lead to rejection or to failure or to crashes or to hang-ups or to undetermined things or to infinite loops, that's okay. If one path does the job, you're good. That thing is part of the language. That input string is part of your language. There's another way to prove this using grammars. Anybody want to take a crack at that? Again, that's an easy proof. Yeah, combine the productions. So have some super start state, a new state, and a new super start symbol, a variable that non-deterministically branches to one or the other original start states of the two grammars respectively. So you have two grammars, each with its own start symbol. Have a super grammar that goes to one or the other. Have two new productions from this new super start symbol to these two old start symbols. This new grammar, basically, and you have all the rest of the productions combined. When you combine the productions, just make sure that there's no variable clashes. You may have to rename the variables. If one production has an A in it and the other production has an A, but they're both variables, make that A prime. Why? Because otherwise you're crossing across this forbidden boundary between the production sets, and you may get things that you didn't expect. Just like when you have two subroutines. If two of you write two subroutines and say, I'm going to use your two subroutines, yours and yours. All right, give me your subroutines, I'll put them in a program. But something can go wrong. If you use the same very global variables as the other person, or even the same name of the subroutine as the other person, now it's going to be ambiguous and clash. Well, one easy fix is I just rename all your variables to some new names that aren't there, and now we're good. How many get that? Simple. All right, so we proved this two different ways. We derived a new grammar for the union by bashing together all the productions from the old two grammars. Or you can do it using a PDA by non-deterministically branching to one of the old ones or the other one of the old ones, and this new non-deterministic PDA will do the job of both and accept the union. How many get all this? Okay, good. It's a bunch. All right. Any questions about that? So we just proved a major theorem that the context-free languages are closed under union. For regular languages, were they closed under union? How many say yeah? How many say no? How many say yeah? That's better. Yeah. Yeah, they were closed under union. How would you characterize the proof for that? 2 words. You have to choose 2 words. Prove in 2 words that the regular languages are closed under union. What was the proof? Or the proof technique, I should say. Was it diagonalization? Was it dovetailing? Was it something else? Which construction? Construction is 1 word. What's the other word? It's good. You're halfway there. Cross product. That's the other word. Cross product construction. How many remember that? Get that? Can see that? Okay. So yeah, regular languages were closed under union. So are context-free languages, but for different reasons. There, it's a cross product construction. States crossed with states, executing 2 things in parallel. Here, you bash together 2 grammars. That's a different thing. All right, we're on a roll. The context-free languages are closed under clean closure, under clean star. Why is that? You can basically derive another grammar for it, right? I'm not sure if... it works, okay. So you have some start symbol that goes to somewhere, okay? So it goes to somewhere, and now there's a whole bunch of other rules, and that's the old grammar, right? The new grammar will have a new start symbol, call it S prime, that will either go to the old one, followed by another copy of the old one, or it will terminate with an epsilon. Let me make that a prime too. All right. So in this new grammar, the new grammar is the old grammar in red plus this new rule in blue. This new rule takes a new start state, S prime. It's not the same as S. It's similar, but it's not the same. So I distinguish it with a prime. That goes to itself and another copy of S, which means if you invoke this rule right here, a lot of times you get a lot of copies of S. And eventually it terminates with an epsilon, which means you can get as many copies of S as you want, 0 or more times. How many get that rule? Which means you're looping over this grammar over and over and over again, juxtaposing, concatenating strings from this language to other strings of this language. And you're getting the clean closure because you're getting any possible large number of concatenations of strings from the red language over and over and over again, concatenated together. And this is a loop here in blue. How many see that this blue thing, this new blue rule right here below the red is a sort of a loop? Okay, good. It's a recursive loop, right? And many copies of S as you want, on and on and on, lots of S's, and finally the S prime goes to epsilon and you have a bunch of S's left. And each one then goes and hits the red grammar with its own individual, separate, independent derivation in the red grammar. So the red grammar plus the blue grammar, whatever the language of the red grammar was, the language of the red grammar plus this new rule in blue, is the clean closure of the red. How many get that? Good. It's a lot of people for just 2 minutes of explanation. That's good. Any questions about that? So we just proved another theorem. The context-free languages are closed under clean closure. Are they closed? Are the regular languages closed under clean closure? How many say their regular languages are closed under clean closure? How many say they're not closed? How many say the regular languages are closed under clean closure? It's a split vote. Interesting. I'm glad I asked because we're getting a split vote here. So think about it for 15 seconds. It's probably not worth more than that. And I'll ask again. Are the regular languages closed under clean closure? Question? Because I want to, he's saying, why can't you have S goes to SS as well as to other stuff? Because S could also have other constructions here below that don't necessarily give you the entire language, just give you some fragment of it. You see, so I don't want to mess with that. I want to make sure that this S prime is different than that S, so that I don't have variable in clashes, or that I don't, so one of these S's doesn't give you some fragment because it can go to other things. I'm not sure if it interferes, but there could be cases where you can get some interference. But because I'm not sure, I'm doing it very explicitly. I'm separating the two completely, giving it a new name. But you're right, you may be able to do that. You just have to kind of think about whether this S may be compound. There may be other rules involving S. S can go to something, S can go to something else. Is that a problem or not? Something that you have to think about. But here you don't have to think about all that. So that's why it's simpler. But he has a very good point. All right, back to regular languages closed under union. How many say yes? Excuse me, closed under clean closure. We're under clean closures here. How many say yes? Yeah, okay, now you're getting it. Why regular languages closed under clean closure? Yeah, but he makes a subtle point. He says clean closure is a large union of things. Sure, it is. And union preserves closure under, regularity. So union preserves regularity. Closure under union, if you have two regular things, union together is a regular thing. But now the clean closure is an infinite union, which is different than a finite union in a fundamental way. So if you can apply an operator a finite number of times to preserve the property, that doesn't mean automatically that if you apply it an infinite number of times, that property will still be preserved. I'll give you an example. If you add two integers together, you get an integer. 1 plus 1 is 2. 1 is an integer, 1 is an integer, 2 is an integer. So addition preserves the property of being an integer. You add 5 integers together, 1,000 integers together, you still get an integer. You add Google integers together, you get an integer. But if you add an infinite number of integers together, you still get an integer necessarily. How many say yeah? An infinite number of integers added together gives you an integer. How many say no? Okay, another split vote. I'm glad he raised that question. See how good that question was? If a question can split a class of smart people such as yourselves, it must have been a good question. So what do you say to that? Infinite number of integers added together. Let's make them 1 for simplicity. Infinite number of 1s added together. What is that? Is that an integer? 1 plus 1 plus 1 plus 1 forever. Is that an integer? How many say yes? How many say no? Now the no's outweigh the yeses, so you're veering toward truth now. Why no? Let's say 1 plus 1 plus 1 plus 1 plus 1 forever was an integer. Where's the contradiction in that? If it was an integer, then what? Then you can add 1 to that integer, and that will be a bigger integer. Does that make sense? And that doesn't make sense, right? Because 1 plus 1 plus 1 plus 1 forever is what? What is it really? It's infinity, right? It's not an integer. Because if it was an integer, it would have a successor, 1 plus it, that would be bigger than it. But now you're saying 1 plus 1 plus 1 plus 1 plus 1 forever plus 1 is bigger than the first sequence. They're both the same. Infinite hotel plus 1 more guest is the same infinite hotel with the same number of guests. How many get that? You can't add a room to an infinite hotel and say now there's 1 more room. It's the same number of rooms as before. Anyway, think about it. But if you have this misconception at this late point in the course, you need to clean it up pretty quickly. Just my advice to you, right? I know infinities are subtle. I know they're tricky, They're not intuitive. That's why we harped on them so much. That's why I gave you as required reading a whole book about infinity called Infinity in the Mind by Rucker. How many actually read that book? Okay, I'm not sure what you're waiting for, but I hoped that you would have by now. Right? It's a required reading. What are you going to save it for the last day of the semester and then read that whole book in one day along with everything else that you need to read? Look, I give you all the benefit of the doubt that you're responsible adults and mature and treat you with respect, but you got to meet me halfway. Don't postpone things that are important. All right, so clean closure preserves regularity and it preserves context free, but it doesn't. Clean closure. Let's go back to the clean closure in regular language. So it doesn't preserve regularity because the infinite union preserves regularity. Infinite union doesn't preserve regularity. It preserves regularity for another reason. That you can take the finite automata from all the final states, cycle back to the initial state, and that's why you can loop around and preserve clean closure and regularity, is preserved by clean closure. That's why. Prove to me that an infinite union of regular languages may be not regular. Yeah, so we already mentioned, and soon we'll prove, that a to the n, b to the n is not regular. But a to the n, b to the n is nothing but the union of ab and aabb and aaabb, all taken together as singleton languages with one string in each language, and it's an infinite union. Let me give you a more dramatic example. Take the halting problem. The halting problem is a bunch of descriptions of Turing machines or algorithms that don't halt. But you can recouch the halting problem language, instead of one infinite set of descriptions of machines or algorithms or C codes that don't halt, take each machine or C code description as a single string in its own language, in its own braces, and union that with the next description and the next description. You have an infinite number of descriptions, each one a singleton language with a single string, each one being regular. But the infinite union of all these regular languages that have single string in each is the halting problem. And the halting problem is not just not regular, it's not even decidable. That's worse. How many understand that argument? So be careful. When you get to infinities, be cautious. Don't make a reckless intuitive leap as if there's no difference between infinity and some number. It's a different object altogether with a different type, and it doesn't behave the same way as finite things, like the infinite hotel. If you have a finite hotel, you can't pull that trick. You can't accommodate another guest and another guest and another guest forever, no problem. Right? You'll run out. With infinity, you don't run out. You can always get one more. That's a dramatic example of how infinities behave differently than finite quantities. That's why we harped on it so much in the course. So if you haven't intuited by now why we spend so much time on infinities and infinite hotel, because now you see where the misconceptions lie. You're stepping on these minds now. That's okay. That's why we're here. To disabuse you of these misconceptions, to make your mind more rational, not allow you to jump into contradictions so quickly, like you may have before. Any other questions so far? Yeah. So why does clean closure preserve context freeness or regularity? So regularity, well, there's a couple of reasons, different proofs you can give. One is you take the machine, go from one of the final states to the begin state, and now it can cycle on itself as many times as you want. Remember that proof when we constructed a machine that, we took a machine and massaged it into a new machine that accepts the clean closure of the first machine. So we proved that some weeks ago. Basically, you cycle with new edges from all the final states back to the initial state and keep cycling as many times as you want, and finally you accept something that's in the clean closure because you can loop as many times as you want, do as many unions as you like. And then, another reason is, remember the definitions of regular expressions. So for every regular language, there's a regular expression that corresponds to that regular language. So you can take that regular expression corresponding to that regular language, put a star over the whole thing. Now you got the clean closure, and that's one of the okay rules for a regular expression. You don't put a star on a regular expression and get another regular expression. It's one of the rules for building up regular expressions from smaller regular expressions. Put a star on it. So you see, you have a regular expression, and then there's another finite automata that accepts it. So starring preserves regularity. Let's put it that way. Good question. So now you have two different proofs. Of course, you had them before too, but now here they are explicitly again. Okay, but at some point things begin to fail, and they don't fail yet. You don't get the idea that everything is closed under everything else. But context-free languages are closed under intersection with a regular language. In a minute, we'll prove the next amazing theorem that they're not closed under intersection with each other. But under intersection with a regular language, context-free languages are closed. So basically, it's a cross-product construction. So you run the pushdown automata, and simultaneously you run the finite automata. You cross the two state sets of the pushdown automata and the finite automata. You run them in parallel on the same input, and you accept if and only if both accept the input. So you're accepting the intersection of the two. Because you only accept if both accept. That means it's in both of their languages, which means it's the intersection of their languages, which means you're accepting the intersection of their languages intersected together. So it's a cross-product construction. How many see what's going on here? Not enough. Ask me questions. So what are we trying to prove? That context-free languages are closed under intersection with a regular language. So you have a context-free language, you have a regular language. They're both sets. They're sets of what? Animals, minerals, or vegetables. What are the sets of? Strings. Let's make sure we have the type straight in our head. If you know the type of something, you have no idea what that something is. Right? Think about it. If you don't know if something is a mammal, you have no idea if it's a zebra or a giraffe. I'm just saying. Okay, so you have a context-free language, you have a regular language, you bash them together, take the intersection. Why is the intersection also context-free? Because you can take the PDA and you can take the finite automata and run them parallel simulation together on the same input stream in a cross-product construction. As one changes states, the other changes states, and you're going from superstate to superstate as pairs of states with a super transition function that does what both transition functions do, one for the PDA and one for the finite automata. And you accept if and only if both accept. It's like running two functions in parallel. The result is still a PDA. Remember what happened when we crossed two finite automata? The result was a finite automata. How many remember that? The cross-product construction for finite automata. It's just another finite automata with a lot more states, perhaps, but still just another finite automata, and therefore its language is regular. That's where regular languages were closed under intersection. Here we're doing something slightly more sophisticated. We're crossing not just two finite automata, we're crossing a finite automata with a pushdown automata. But the construction is very much the same as before. You cross all the states with all the other states, all the states of one with all the states of the other. You mark as super final states all states which have final in both, little ovals with two dots in each. How many remember that slide from 30 or 40 slides ago? Cross-product construction. I'm not getting a lot of warm, fuzzy feeling here that people are remembering or knowing what I'm talking about. So ask me questions. You want me to repeat it a couple more times? I'll be happy to do it. Yeah. 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 Yes. Yeah, very good question. So he's saying, remember that language that was A to the N, B to the N, the pumping lemma? We mentioned that it's not regular. How many remember that? Good. This is a good number of hands. So that was not regular, but now he's saying, well, yeah, it's not regular, but isn't it context-free? Because you can recognize it with a stack. How would you recognize A to the N, B to the N using a stack and a PDA? Yeah, let's see if somebody else can get it. How would you recognize A to the N, B to the N using a PDA, i.e. a finite automata with a stack? Because we already know a finite automata by itself can't do it. Pumping lemma argument. Right? Essentially pigeonhole principle. Yeah. Yeah. Push all the A's onto the stack. Then when you see the first B, then pop all the A's against the B's one at a time, one pair at a time, until you know that they match in number. And if they do, if and only if, you say, okay, I accept. If there's a mismatch, if there's too many A's or not enough B's, or too many B's and not enough A's or whatever, reject. How many see that will accept A to the N, B to the N with a stack? Okay. Still only half the class. I'll give the other half the benefit of the doubt. Don't want to put anybody in a spot by calling on people, obviously. But I hope it makes sense, these kind of arguments now. You have a lot of abstractions under your belt. If you solve even a modest amount of problems along the way, these things should kind of begin to flow at this point. Right? So, yeah, so A to the N, B to the N, therefore, is a context-free language, is what we just said. Because we just described how a PDA would do it. And PDAs, context-free languages, they denote the same class of languages, the context-free languages. Another question. Yeah, so he's kind of jumping ahead to the next theorem. He says, why does this cross-product construction work here, but doesn't work in the next theorem when you bash together two context-free languages, or two PDAs equivalently? Why can't you simulate two PDAs in a cross-product construction? And the answer is, because you'll need two stacks, one for each. And one stack by itself is not going to cut it. One stack cannot simulate two stacks. Because if one stack wants to push and one stack wants to pop, what's the simulation stack going to do? Push, pop, something else? It's not clear. That's not a proof, it's an intuition. The proof is that 0 to the n, 1 to the n, 2 to the n is not context-free. And it's the intersection of two context-free languages. Let's not harp on that last sentence too much. I just gave you a preview of what's coming up next. But backing up, if you simulate a PDA, a pushdown automata, and you simulate together with it in a cross-product construction a finite automata, one uses a stack, one doesn't. So the simulation just needs one stack for the one that has a stack. And for the one that doesn't have a stack, the finite automata, it doesn't need a stack. So the simulation is just another PDA that simulates both the PDA and the finite automata together in a cross-product construction running in parallel on the same input. So a single PDA can do the job of simulating another PDA and a finite automata together, because the finite automata doesn't need a stack. The PDA does, but you got a stack because you're another PDA, the simulator. How many understand it now? It's a little more. Good. But when you try to do that with two context-free languages or two PDAs, the stacks begin to clash if you try to simulate them with a single stack. That's not a proof, it's an intuition. But you can't get it to work. So context-free languages are not close under intersection, it turns out. Yeah, maybe in a couple of slides we'll show an example. I already mentioned the example. 0 to the n, 1 to the n, 2 to the n, or A to the n, B to the n, C to the n. That's not context-free, turns out. But it's the intersection of two other context-free languages. It's the intersection of A to the n, B to the n, C star. And A star, B to the n, C to the n. How many see what I just said? I can write it down. So I'm saying that A to the n, B to the n, C to the n is equal to the intersection of A to the n, B to the n, C star, and A star, B to the n, C to the n. How many believe this is an equality? Think about it for 10 seconds. How many believe now it's an equality? I was hoping for at least half the class. That's okay. So what is this first language here? Equal numbers of A's, B's, and C's juxtaposed. How many get that? That's what it is. Simple. All right. What is this language here? Equal numbers of A's and B's, and arbitrary number of C's following. Right? What is this language? Arbitrary number of A's followed by equal numbers of A's and B's. So if you intersect strings of this form with strings of that form, you got to have equal numbers of A's and B's and any number of C's you want. And here you have equal numbers of B's and C's. By transitivity of equality, now the number of A's and B's and C's must be equal to each other. And therefore you get the language on the left. And so it is an equality. How many C's now? Good. Okay. Thank you. Relieved. Okay. It turns out that this language is not context-free. We haven't proven it yet, but we'll get there. For the midterm, you don't have to worry about why this is not context-free, but it'd be nice to know that it is, just in case you need to use it somewhere. I'm not saying you will, but in case. Now, why is this context-free and why is that context-free? Both sides of the intersection. Why is A to the n, B to the n, C star context-free? It's not complicated. With one sentence, you can answer it. Yep. Yeah, so you can recognize this language by itself, A to the n, B to the n, C star, by pushing A's and popping against the B's and then flushing the C's. You don't care how many C's you see. That'll do the job. That's a PDA. So this language here, A to the n, B to the n, C star, is context-free. How many of you see that? Good. This language here on the right, flush the A's, push the B's, pop against the C's. Make sure they're an equal number. End of story. You just accepted that language. You're a PDA. You just need one stack. You're good. So this language here is context-free. This language here is context-free. Their intersection is equal to that, and that isn't context-free. So that's a counterexample why context-free languages are not closed on their intersection. Because if this makes the theorem fail, then it's not a theorem. It's a counterexample. You just proved by a single instance of a counterexample why such a theorem, if it was closed on the intersection, would fail. So it's not closed on the intersection. Now, I'm not saying it's never a context-free. If you take context-free union with a context-free, I'm not saying it's never a context-free. I'm not saying it's not always a context-free. Never is not the same as not always. How many understand that statement? Good. Yeah. It achieves the fact that I want the intersection of two context-free things to be non-context-free. And this is my target non-context-free line, because I know this is not context-free. We haven't proven it yet, but I'm telling you it isn't. Take my word for it for now. So how do you get this language to be represented as the intersection of two context-free languages? This is one way to do it. By saying the A's and the B's must match, and separately saying the B's and the C's must match. And all strings where the A's and the B's match and the B's and the C's match must have all A's, B's, and C's match. Because these two conditions create this condition by transitivity of equality. How many see that transitivity of equality is at work here? What did I just say? Transitivity of equality. What do I mean by that? Let's nail it down so it's not just some fuzzy words that sound good. What do I mean by transitivity of equality? When the equality operator is transitive. What did I just say? Yeah. Yeah, it's just a transitive property of equality, but at the risk of maybe coming up with a different sentence, it doesn't use exactly the same words that I did. What does that mean? Yeah, exactly. If one thing is equal to a second thing, the second thing is equal to a third thing, then the first and the third are also equal to each other. Things that are equal to something are also equal to each other, is what he's saying. That's transitivity of equality. Some operators are not transitive. Give me an operator that's not transitive, just to belabor this point, so you don't think everything is transitive. Anyway, think about it. Some operators are transitive, some are not. Fine. And finally, this one now is relatively easy, because it says that the context-free languages are not closed under complementation. Before we even tackle that one, are the regular languages closed under complementation? Repeat. Are the regular languages closed under complementation? You take a regular language, complement it. Do you necessarily get a regular language back? Yeah, you do. Why? Yeah, take the accept state, and flip it. Take all the accepting states, make them non-accepting. Take the non-accepting state, make it accepting. That flipped or negated finite automata does the opposite of what the old one used to do, which means it accepts the complement of the original language. Why can't you do that trick with PDAs? Why can't you take a PDA and pull the same trick, flip the accepting and non-accepting states, and say, okay, now that accepts the complement of the original PDA? What's the problem with that? Because you have a stack. It's not just about states, and the stack can complicate things. That's an intuition. The stack can get in your way, but it's even more fundamental reason than that. I mean, what does it mean to complement the stack, right? It's not clear. And the stack interacts with the states in a fundamental way. If something on the stack is different than before, you'll go to a different state, not the same state that you went to before if the stack was something else, right? So, and what does it mean to complement the stack now? It's kind of undefined. So you might think, well, maybe there's some clever way to complement a stack, whatever that means, and get the job done. And the answer is no, you can't. You still can't do that. Another way to intuit this is non-determinism gets in your way. When you have a computation that's deterministic, it's one path, state change, change state, end up somewhere, accept, then you can convert that accept to a reject. If it's a reject, convert it to an accept. It's pretty easy how to complement a single path of a computation that's deterministic. But how would you complement a non-deterministic tree-like computation? Some paths lead to an accept, some lead to a reject. As long as there's one accept, you're good, you accept. Doesn't matter if there was a lot of rejections. Life is kind of like that. You can try a lot of things, as long as you succeed once, you're good. If you find your life soulmate, you'll be happy. If you find the best job, or one good job, you'll have a living. You don't have to succeed at everything you do. You have to succeed at least one thing, and then you'll still be good, right? So, non-determinism has this property that as long as you succeed somewhere, the whole thing is good. We don't care about the failures. But how do you negate that? Do you make that branch and success a failure, and the failures make them successes? Will that do the job? No. Another way of thinking about this, non-deterministic tree computation is like a there exists operator. There exists a path that does the job. If you want to negate it, there exists. Does that mean there doesn't exist? What's the negation of there exists? If you say there exists some object that has this property. There exists an x such that P of x is true. And now you want to negate that. What does it mean to negate this? Does it mean the following? There exists an x such that that property doesn't exist? Is that equivalent to that? No. How many see that it's not the same? But so what is it then? How would you negate that there exists? Yeah. You have to go into the other quantifier. You have to go from the existential to the universal quantifier, right? Now you can say for all x, P doesn't work for x. And that is equivalent to the negation of the first. So here we have an existential quantifier could represent a non-deterministic computation where there exists a path to success. But that means the complement of that is that all paths must fail. So if you negate the original tree, you won't get the tree that you want. So if you negate the original tree of the non-deterministic computation, you won't get a tree that says everywhere there's a failure. Because think about it, if one of the paths succeed and others fail, if you negate that, you'll have the same property. Some paths will still succeed and some paths will still fail. How many see that? You change the fails to succeeds and it succeeds to fails, and you still have some of each. It wouldn't be the other one where all must fail. So negating a non-deterministic computation doesn't get you the negation that you so desperately crave, right? You can't negate non-deterministic computations and expect to see their complements. Those aren't the droids you're looking for. Okay. So, bottom line, complementation doesn't work, but those are not proofs. Those are intuitions. What's a proof? One way to prove it for sure is that you can use De Morgan's law, right? What do I mean by De Morgan's law? Anybody want to take a shot at that? De Morgan's law, yeah. 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 So you can say, A intersect B is A complement, B complement, union, complement again. Right? How many get that in green right here? Believe that. That's De Morgan's law for sets. Right? But we already know that things are closed under union. Right? That's the first theorem. We know that they're not closed under intersection. That's this theorem here. 1, 2, 3. That's the fourth theorem right here. It's not closed under intersection, but it is closed under union. But suppose it was closed under complement as well as union. So if the complement preserve context freeness, we already know that the union does from this theorem here, from the first theorem. So if it was context freeness was closed under complement, then A bar, the complement of A would be context free. The complement of B will be context free because we're presuming towards contradiction that it's closed under complementation. We already know it's closed under union, so the union of A bar and B bar will still be context free because it is closed under union. We don't have to presume it is true. That's the first theorem we proved. And then again, it's closed under complementation, so the complement of the union of the complements will still be context free. But altogether, these operators give you A intersect B by De Morgan's law, and we know for sure as a theorem that they're not closed under intersection. And here's a counterexample, right? So they can't be closed under complement either by De Morgan's law. How many understand this argument beginning to end? Okay. You want to ask me questions? It's important. Yeah. Okay. So how many people buy this identity as true, the green one? Good. But what does it say? It says that the intersection of two things is the complement of the union of their complements. That's what it says. Union preserves context freeness. So if complementation preserves context freeness also, if it would have preserved context freeness also, complementation would, then the whole right side will be context free. But the whole right side is equal to the whole left side. And the left side is sometimes not context free like this blue example down here. So therefore something went terribly wrong. One of our assumptions was way off, and the only assumption we made is that complementation preserves context freeness, so it doesn't. And there's another argument why it doesn't, besides the fact that you can't just complement a non-deterministic bifurcating, computation. It's not a path but a tree, and on and on and on. With this existential quantifier becoming a universal quantifier, and blah, blah, blah. All right, so we proved what? 5 theorems on one slide. That's pretty good. Yeah. It could. If the PDA is an FA, yes, it would. How can a PDA be an FA? How can a pushdown automata actually be a finite automata? Easy question, yeah. Empty stack, but let's get to the real core of the issue. Yeah, the stack will remain empty, but what else? Yeah, the stack is never used, and that's why it's empty. So it's not just because it happens to be empty, and sometimes it may not be empty. It will always be empty. It will never be touched or used. So if you have a PDA that never touches its stack ever, no matter what the input is, it might as well be a finite automata. if you have an airplane that never takes off, it's a car or a bus, if it's really large. How many get this? Okay, good. Any other questions? Yeah. So he's saying, is a second proof for this that you try to combine two stacks and you won't succeed, basically, because they'll clash. One of them will try to push, one will try to pop. So if you try to combine together and simulate a combination with a single stack, what does that simulated super single stack does when one of the substacks that it's simulating tries to push, another tries to pop? That's an intuition, but it's not quite a proof. Why is it not a proof? Because maybe there's some clever way to simulate two stacks using one stack that we haven't thought of. Some omniscient entity that's all-knowing, will come by and say, here's how you do it. Too bad you didn't figure it out because you're mortal. And you could be geniuses, but not omniscient. No, there doesn't exist a method whatsoever, not even in theory, for anybody to discover, however omniscient. So it's worse than we don't know how to do it. It can't be done. Same for an integer between a quarter and a third. There is no integer between a quarter and a third, and if you take $1 billion and 1,000 mathematicians and put them on this project, they won't be able to come up with one either. It ain't there. That's what we're saying. So it's not the kind of proof saying, I can't think of an integer between a quarter and a third, give me a week and maybe I'll come up with one. You don't have to take that risk, that somebody will come up with one if they're smarter or spend more time on it. It ain't there. That's much more decisive and strong and deliberate kind of a statement. It's a bold statement to make. So if you say there's no PDA that does the job, you can't just say there's no PDA that does the job because here, I'll try to make a PDA that does the job and I can't. That's my proof. Right? You see why that's not a proof. It just means you can't find one. It doesn't mean that somebody omniscient can't find it. You have to be a lot more exhaustive than that. That'll be like saying, I can prove to you that I'm not a millionaire. Here's my bank account, it's got $7 in it. There, I'm not a millionaire. You happy? No, you're not happy, because you haven't covered enough ground. Maybe some investigator will work long and hard and discover that I own some, chain of islands in the Bahamas that are worth a lot more than $1 million. It just wasn't obvious. It was under some assumed name, whatever. How many see the point of all of this discussion? Good. You have to be careful, not jumping to conclusions that could be undermined easily by a much smarter entity than yourself. You have to really be exhaustive when you prove non-existence. So here we're trying to prove that we're not a millionaire. That's hard. We're trying to prove that something doesn't exist. Right? That if you take the complement of a context-free language, there doesn't necessarily exist another context-free language that is equal to the complement. In general, there isn't. So this does the job. De Morgan's law is decisive. There's no way around that. That's an ironclad argument. All right. Now, remember what we did for regular languages and finite automata? We said, could you determine if a finite automata accepts the empty language, an infinite language, whatever. If the difference between two languages that are regular is also regular, if they have any strings in common, all these algorithms that we did last time. So let's try to do a few like that. I give you a Pushdown Automata, ask you, is its language empty? Is that decidable? Is there an algorithm to determine whether the language of a PDA, a Pushdown Automata, is empty or not empty? So I'm giving you sort of the parallel kind of questions for that. Is the language of a PDA finite? Is it infinite? Is a particular string an element of the language of a given Pushdown automata? And of course, you can ask the same questions about grammars, because grammars and Pushdown automata are equivalent. We already said that. And so you can ask the same analogous questions about not just machines, but also about grammars, just like you could ask the same questions about finite automata, but also about regular expressions or regular languages in general. So for extra credit, answer as many of these algorithms as you can. These parallel the algorithms we talked about last time about finite automata in regular languages. Now, can anybody tell me this problem in particular, the last one, if I give you a grammar, context-free grammar, and I ask you, is this string generatable from that grammar? Is it an element of the language that the grammar generates? This last question here. How many understand that question? I'll give you a grammar, it can generate lots of strings, and I'll give you a string in particular and say, is that one of those strings that the grammar generates? That question actually is so useful, so practical, so famous, and so ubiquitous that all of you have tried to solve that question probably thousands of times by now. In fact, some of you have tried to solve this question today. So my meta question to you is, what am I talking about? When have most of you tried to solve that last question over and over and over again, thousands of times already, and possibly even multiple times today? Somebody who hasn't spoken yet today. The same 10 people impress me, which is good, but I want more people to participate. And I don't want to put people on the spot by calling on you, because I can just point to people and call you, but I don't like to do that. I'm your buddy, not your adversary. Right? I don't want to rile you up, but I want more people to participate too, so help me out here. Yeah. When we talk to one another, interesting. Any other thoughts? So the grammar would be like the English grammar, right? You know what? That's a good answer. It's a subtle answer. Saying when you talk to each other, you have the grammar of English. It's a complicated grammar, but it's a grammar. The question is it a context-free grammar? That's a much more subtle question, actually. But suppose it was a context-free grammar. So when we talk to each other, what are we trying to find out? How are we answering that last question? It's an interesting point, very good point. Somebody gives you a sentence, says something to you, like I just told you. I give you a sentence, stop with a period. So you're trying to figure out if my sentence is grammatically correct, and it's part of the English grammar, and the language that you're trying to match it against is, or see if it's a member of, is all grammatically correct English sentences, generatable or derivable from all the proper rules of English grammar. All right, but let's put that aside for now. It's a very good answer, but let's put it aside and try to come up with something that's more computer science-y rather than natural language, although I really like that answer. You see, you speak up and you win. You're a hero. Yeah. Yeah, I'm talking about code. So where is the grammar and what's W? Yeah. So the grammar is the syntax rules of your programming language, like the syntax rules of Java or C or Python or C++ or whatever is your favorite language. This is a bunch of syntax rules, right? How do you form loops and what keywords do you use to denote arrays and types, whatever, braces and commas and semicolons. Those are the rules of the language. It has, programming language has a definite syntax. It's not just willy-willy, nilly-willy juxtaposition of random characters. What is W in this context? Your code, like you said, either a line of code or several lines of code. And what tool do you use to determine whether that is a member of that? The tool has a name, it's a single word. You want to buy a vowel? Yeah. It's a compiler. Every time you run a compiler, you're answering this question. How many see that? Good. And of course, we speak English or any other language too. You're sort of implicitly answering that question. So some of these questions are not just, they're so ubiquitous, you're actually using them over and over and over again every single day of your life as computer scientists. Now, just so you don't think that everything is decidable, by the way, all of these are decidable. There's algorithms for all of these. If I say find algorithms for all of these things, I'm not kidding. I'm saying there are algorithms for you to find. But other properties of PDAs or context-free grammars do not have algorithms. So if I ask you, is this PDA that I'm giving you minimal? Is it possible to minimize and make it smaller and still preserve its function? Give you an equivalent but smaller PDA that does the same job as the first. Like minimizing a finite automata, we saw how you can do that. That was not just decidable, it can root n log n time, actually. PDAs you cannot minimize. It's undecidable. There's no algorithm in the universe, not for anybody to discover, ever, that takes a PDA and comes up with an equivalent smaller PDA. Don't get me wrong, for some PDAs it's possible to do. I'm just saying it's not possible to do all the time for all of them with a single algorithm. That's what undecidable means. It doesn't mean, if the halting problem is undecidable, that doesn't mean that you cannot tell ever if a program halts or doesn't halt. If I say begin, end, that will halt. There's not much to it. And that's the instance of the halting problem. But other instances are much, much harder than that. If I give you two PDAs, two pushdown automata, and I ask you, are they equivalent? Do they accept the same language? Undecidable. There's no way to do that. You can prove all these things. If I say, here's a context-free grammar, is it a minimal grammar? It has the least number of symbols or variables in the grammar. Undecidable. Is the language of two grammars the same? Is the intersection of the languages of two grammars the same? Is it empty? Undecidable. So all these are undecidable. Ambiguity we'll cover maybe after the midterm. Don't worry about that. It's a bit subtle. So again, for extra credit, not necessarily anytime real soon, maybe wait after the midterm, I'm putting a bounty on each and every one of those. Prove that each one is undecidable. Now, certain enhancements to PDAs make them more powerful. So for example, if the read-write head can go both left and right, that gets you more power. That's a superpower. So for example, why is it that if you can go left and right on the read-write head of a PDA, you all of a sudden can do things that you couldn't do before? Give me an example. Give me an example of something that's not context-free, language is not context-free, but a two-way PDA can recognize it nevertheless. If you can't do it in 10 seconds, I'll give you an example. Any takers? Yeah. Yeah, excellent. So that language from before, let's see if all my chicken scratches are here. Yeah. So this language, A to the N, B to the N, C to the N, right there, we said it's not context-free. But if you have a two-way PDA, it can recognize it. Why? Because push the A's, then pop against the B's, go back to the beginning of the B's using the two-way capability, backtrack over the B's, then push the B's and pop against the C's. Now you got it. By transitivity, now all A's and B's and C's are in equal numbers because you match the A's to the B's and separately you match the B's to the C's. But the only way you can do this is by backtracking over the B's. So you have a two-way PDA that just did the job that a regular PDA can't do because that's not context-free. How many get this proof? Okay. Any questions? So you see now we have a lot of infrastructure in our heads, a lot of concepts, techniques, hopefully. Now we can prove a lot of things in quick succession. Think about trying to do this at the beginning of the course. It'd be hopeless. But now we have a lot of oomph, a lot of mojo in terms of techniques and interactions between these ideas and reductions, and using dovetailing and diagonalization, using power set constructions and using cross-product constructions and converting machines to grammars and on and on and on. There's a lot of constructs, ideas, techniques, proof types that we can use and apply. I'm not saying it's trivial. It isn't. It's tricky business, but at least now you have a big set of power tools at your disposal, and you can prove a lot of things in quick succession. Yeah. Good question. So you're saying A to the N, B to the N, C to the N, D to the N, E to the N. What is that? That's still not context-free, but is it worse than not context-free? It turns out it's as hard as A to the N, B to the N, D to the N, essentially. Yeah. So if you have A to the N, B to the N, C to the N, D to the N, E to the N, how would you recognize that with a two-way PDA? Very similar to what we just did. Push the A's, pop against the B's. Backtrack over the B's. Then push the B's, pop against the C's. Backtrack over the C's. Push the C's, pop against the D's. Backtrack over the D's. Push the D's, pop against the E's. If everything works out, you accept. End of story. How many got that? It's a very good question. And of course, a regular PDA couldn't do this, any of it. All right. So what about two stacks? If a PDA had two stacks, not one stack, but two stacks, and in the obvious way would be using two stacks independently of one another. You can push to one, pop from the other, pop from the first, push to the other, pop on both, push on both, do nothing to both, whatever you'd like, independently of each other, two stacks. Turns out that's a superpower also. That gets you things that one stack cannot possibly do. What do you think an example would be? Give me an example of a language that can be recognized with two stacks but not with one stack. Same thing. How many see the same thing? So you're getting a lot of mileage out of this little language, A to the N, B to the N, C to the N. So remember that language is getting you a lot of dividends, and it'll get you a lot more too. Maybe even on the midterm. Not sure because I haven't made up the midterm yet, but it's a good language to remember. How would you recognize using two stacks, A to the N, B to the N, C to the N, in one sentence? Even simpler than that. Let's just do it brute force simple. Forget queues, forget simulation. I mean, yeah, you could do that, it will work, but just something simple. Yeah. Yeah, put all the A's in one stack, put all the B's in another stack. Pop them both against the C's, end of story, right? How many see that solution? So two stacks, you can do a lot more. It's a superpower. It enables you to do things that you couldn't do with one stack. And of course, if you have a queue, same thing goes. If you have a queue, you can do even more stuff with a queue. I'll leave that as an exercise, But with a queue, you can recognize not just A to the N, B to the N, C to the N. You can recognize any language that Turing machines can recognize. That's a bold statement right there. For extra credit, prove it, that a queue can simulate any Turing machine, actually. If you have two heads that both go left to right, so it's not a two-way, but you have two heads that both go one way, you can still recognize A to the N, B to the N, C to the N. To take one head, put it right over all the A's until it hits the B's, then march them in lockstep to match the A's to the B's. Now one will be at the end of the A's, the beginning of the B's, one will be at the end of the B's, beginning of the C's, and march them in lockstep again, comparing pairwise, and it's A to the N, B to the N, C to the N, you just recognize. How many see that? Good. Any last minute questions? So you see how you can now quickly prove in quick succession lots and lots of theorems from all the stuff that you know. It's good. All right. I'll be in touch by email about the midterm.